So Salman Nazir obtained his PhD in electrical and computer engineering from the University of Michigan, Ann Arbor. Go Blue. He's currently a senior engineer at Quanta Technology, where he contributes to the development of advanced analytics and algorithms for integrating DERs into power systems. Okay, feel free to start.
Thanks, Johanna. So I'm Salman, did my PhD at University of Michigan, work with Dr. Ian Hiskens. Today I'll be talking about analysis of synchronization in load ensembles. So thermostatically controlled loads such as air conditioners, electric water heaters, refrigerators are widely popular in terms of their features for controllability and the virtual storage they can provide. So very qualified for providing demand response services. Many coordination schemes have been proposed, and thanks for the previous presentation, which also sets up the context nicely for this work. We noticed that in many literature, there has been concerns about TCL synchronization under different control schemes, and wanted to explore that in more detail. So the reason we worry about synchronization is synchronization can lead to increased fast cycling on-off behavior of TCLs and also lead to undesirable power changes, can lead to poor controller performance. So if you are confined in a very narrow temperature zone after some control steps, then you really have narrowed your controllable space, and the reachable space has also reduced significantly. So that's why we need to study the general techniques of identifying the synchronizing behavior, how fast that might appear. And in this paper, we propose a eigenmode based analysis technique. So as the previous presentation was also discussing about a TCL, cooling TCL turns on and cools and then turns off and heats due to ambient. So it has this dead band and temperature moves within that dead band. So different kinds of coordination schemes have been proposed: randomized switching or probabilistic switching, priority-based switching, transactive or market-based coordination schemes where TCLs are offering some kind of price based on their temperature and comfort, and then also temperature set point variations where the dead band can be moved up and down to provide some capability in power variation. So the aggregate dynamics of TCLs can be modeled as Markov chain type model with Markov chain type model. So in this case, as TCLs heat or cool, they move from different discretized temperature bins to different temperature bins. So the on-off states are also captured. So TCLs have their probability distributions evolving over this bin space. And simple representation can be obtained as x dot is equals to ax, where a is a linear time invariant matrix, assuming that it remains fixed for a while. And there has been several papers in literature that have looked into many detail of this model, how to develop how to obtain the coefficients of this model, and so you can refer to any of those. So in this work, what we focus on is if we have the bin width and the temperature on-off rates, then we can compute the coefficients analytically, and then we can also obtain a discrete time representation because knowing the sample time, we can simply take an exponential of the continuous time A matrix. So now, given that we have the dynamics, we can also design the control. So if we have this bin model, then all the off portions of the bins, we can assign these on and off fractions to these TCLs. So if we send the off fraction, then many TCLs in this bin can respond by switching probabilistically and going to the on bins, and similarly for the off portions. So if a state is known at x minus, then knowing the fraction, we can compute approximately what fraction will be, how the distribution will evolve right after the reset condition. So similarly for priority or market-based scheme, we can have a switching surface of B clear. So all the bins that have temperature above be clear have higher temperature, so they want to cool fast. They want to cool, so they have higher priority. We can map it to price and also show that the offer price can be higher for those, and they will dispatch first, and then all the ones below these would dispatch next, would turn off during that interval. Knowing that map, we can next design um, hybrid representation where the continuous dynamics is given by x dot a equals to ax, and b is going to be the control update matrix. So at discrete intervals, we are going to change the B matrix. So at tau, 2 tau, such intervals, we'll update the B matrix, and the output is also captured by y equals to cx. The discrete time, a discrete time representation can be obtained from this for the state evolution right after or right before the resets. So just but if we define of t as the states right after the reset, a to the tau will propagate it forward, and then b of t would apply the control. So the states at discrete time would propagate with bk a to the tau xk in this form. So knowing that, now we can make some assumptions. That let's first assume that the B matrix is fixed for a while, and if B is fixed, then B a to the tau is going to govern the dynamics of the states right after the reset. The matrix A, we will capture the eigenvalues and order them. So we have lambda 1 to lambda 2n as the eigenvalues, and v1 to v2n are the corresponding eigenvectors. So if we define the initial state in terms of the eigenvectors and how they span those eigenvectors, we can derive the coefficients easily, and then we can write a modal decomposition where xk is a to the x naught. So simple algebra will find that this is written in terms of the modes of the system. So having the lambda, ci, and vi, we know how the modes will evolve over time. And the modes can also be complex, and they would appear as complex conjugate pairs. So so knowing that this is a Markov chain type model, one property that's really comes out is that in every case we'll have a lambda 1 equals to 1. So the largest eigenvalue is at 1. So we'll have the steady state of these distributions always converging to C1 V1. And this is shown in this figure. The first mode is showing the steady state. The other three modes are also shown. And then if they are complex, only the real parts are shown. So the mode governs the steady state behavior of the TCLs. The other modes are governing the transient behavior. So from the modal analysis, we can also obtain some convergence guarantees and get an idea of how fast the convergence is happening towards the synchronized state. If all the eigenvalues except the first one are less than 1, then with increase of the time step k, the eigenvalues would converge to 0. So the effect of the eigenvalues other than 1 would disappear very fast. So if lambda 2 is large, then the effect would stay, but if lambda 2 is small, then the effect vanishes really fast. So in Markov chain literature, this is also known as spectral gap. 1 minus lambda 2 is known as gamma, which is defining how fast the chain mixes and converges to the steady states, and large gaps indicate faster convergence. So instead of trying to always visually inspect the synchronization behavior, which will appear in a distribution after applying control, we want to have some metrics that can be easily quantified and we can measure them quite easily. So in this case, we define all the bins that have non-negligible quantities in them in the density of the TCL distribution, and then we can define the maximum fraction in a bin, the bin spread, the bin range, and the composite index that will be the multiplication of these three indices. So if we have all these indices bounded between 0 to 1, the composite index is also bounded between 0 to 1. So next we'll start looking at some results. So we vary the control duration, tau, and we change the market clearing price, which reflects into the clearing surface B clear. And then we look at the synchronization index and see how the different cases compared. So in this case, in the x-axis, we are also changing the parameters. When the ambient temperatures change, alpha 0 and alpha 1, the heating and cooling rates are changed. So this shows as the ratio of alpha 0 over alpha 1 is changing, how the synchronization index is changing for each of these cases. So what we observe is that when we change the control update interval and allow longer duration, then TCLs have more time to get dispersed from the clearing surface. So naturally, they would be more dispersed, less prone to synchronization. But if the clearing surface is near the switching boundary, for example, in this case, near the upper boundary, then the boundaries would cause switching, which would cause TCLs to wrap back and remain synchronized in a narrow temperature zone. So case B, which has the smallest interval and the be clear and close to the boundary, showed the highest synchronizing tendency, and also the spectral radius was also highest for case B. And in general, we are able to vary these parameters and obtain these results really fast because all of these are based on simply changing the B matrix and looking at the eigenvalues and eigenvectors and plotting them or looking at the in composite index variations. So more detail into the case A, as we change the alpha 0, alpha 1 ratio, we see that after some time, the real eigenvalue that was the second eigenvalue is reaching at -1. And there's already another eigenvalue at +1. So what this suggests is that in this case, there's going to be two undamped modes, +1 and -1. And if the initial condition spans both of these eigenvectors, then there will be undamped oscillations in the power. So this is quite interesting to observe in this figure. And then in this figure, we are showing that as we change the ratios of alpha 0 to alpha 1, what kind of distributions are the resulting distributions. We already plotted the synchronization indices, and we know that initially they were quite dispersed, and for this range of parameter values, the distributions were much peakier. For the second case, alpha, where the tau is 10 minutes and the clearing bin is near the boundary, this was the case where the highest synchronization level was observed, and also the spectral radius was the highest. So the convergence to synchronization was synchronized state was also the fastest. The third case was the one that had longer duration and also temperature boundary at the clearing boundary at the middle, and the temperature distributions remained quite dispersed because of the reasons described before. Now we compared the case of randomized switching. So under randomized switching, we changed the fraction of on and off requests and switch between off and on requests every 5 minutes. So during the 5 minutes, TCLs are requested to, for example, go switch to switch more TCLs to the on bins, and then subsequently switch from on to off bins. And this can be captured in this A matrix, where A is applied at every second, so tau is 1, and B off is applied to that. It's taken forward by 5 minutes, and similarly, then periodically B on is applied. So under randomized switching, what we observe is that only for a certain parameter range, the TCLs can show high level of synchronization, and that is when the ambient temperature remains low. At that low temperature, the air conditioners have a much faster cooling rate than their heating rates. So because of that asymmetry in heating and cooling, they move to one side of the distribution, and then they get cornered at that part of the bin space. So if we apply symmetric and fixed up and down power variation signals, depending on the heating and cooling rates, the distributions might get synchronized quite easily. And finally, we can also obtain bounds on the aggregate power because we can obtain the steady state directly from the eigenvectors. We can also obtain the output as y equals to cx and compare the before and after reset effects on the power, and obtain bounds on the aggregate power. And for more complicated periodic signals, that's also possible. We just have to consider the possibilities of B1, B2 applied in different orders, and we can obtain the bounds. So in this case, when a B control vector is applied, we can see how the power variation looks like, and we can see that similar to the case where there was 2 eigenvalues and with value 1, 2 undamped modes. In this case, this leads to sustained oscillations. Moving on to the conclusions. So we presented a technique both based on eigenmode analysis, which can give us indication on if synchronization will appear and determine at what rate it might appear, compared priority-based and randomized switching schemes to understand influence of different parameters on power variation, temperature synchronization, and damping of oscillations. Finally, this method can be extended to quickly assess the benefits and limitations of a given control strategy, and future work could involve extending it to other coordination techniques such as set point variation, or considering additional operation constraints such as lockout. If you have any questions, I'll be happy to take them, or feel free to email them to me. Thanks.
Thanks, Salman. Any questions for him? There's no questions yet in the Q&A.
Okay.
I could ask questions, but I was on Salman's dissertation committee, and so that would be cheating. So, okay, good. There's one. Adil. Can you see it, or should I help?
I haven't, it has not appeared on my screen. Okay, yeah.
So,
thank you for the talk. Can you please elaborate on the system, if system away from the series? Yes, so Adil is asking about the transient versus the steady state behavior. So the transient behavior is going to show up, but we are going to look in this method, we are only caring about the variations in the steady state right at the reset event. So there could be other dynamics within that interval. But if you are interested in capturing more dynamics of states within the reset interval, you can also discretize it further to capture events at the middle of the interval. So let's say if tau is 30 minutes, but you are interested in capturing some of the transient dynamics, then you can just take more samples in the middle, and A matrix you can propagate it that many steps forward and basically observe more. In this case, we just observed the behavior at the reset condition at every tau intervals.
Thank you. Could you also think of ways, so it seems like you're using this for analysis after you've designed a controller system. Could you also use it for the design process? Is there any way to think about how to construct the eigenmodes that you want to avoid synchronization?
Yeah, so one thing we observed is that there is also a significant computational benefit. See that the initial condition spans only certain eigenmodes. Then we can design controllers to see which modes we want to suppress how. So we can only work in that eigenmode coordinates and see how to controllers to suppress particular modes and their behavior. So we just change the coordinates to the eigenmode coordinates and then and see how to design controllers optimally to suppress each of the different modes that we don't want.
Yeah, makes sense. Any other questions? Okay, so we're pretty much at time. So if you do have questions for Salman, he has his email here on the slide deck. So thank you, Salman,
Thank
for the
you.
great presentation. Oh, Matt says, what was the most surprising thing you learned, maybe? That's a good question.
So the most surprising thing was that we were able to catch this period adding bifurcation behavior. So typically we had to run time domain simulations many times and change parameters to see when you change control parameters, when we observe kind of like period doubling of TCLs, like or if sustained oscillations would be guaranteed to exist or not. And this method can just quickly, based on eigenvectors, give you a guarantee that there is going to be a steady state with undamped oscillations, or it's going to have all the oscillations died out in steady state. So that was quite interesting, and can identify how many eigenvalues are going to plus and minus 1 and will be undamped. So how many undamped modes are we working with? That also helps in understanding what kind of periodic behavior will be observed in this ensemble.
Great. Okay, well, thank you very much. And thanks to everyone who presented in the session and to everyone who was asking great questions. I think it went really well. If you're interested in more on this topic, there's a session tomorrow on aggregation of distributed energy resources that has some talks that have some overlap with the themes that were presented here. So thanks to everyone, and see you on Zoom.
Thank you.
Thank you all.
Bye.
Goodbye.
Thank you.
Bye.